let's get started. So I think we've heard it a few times already today that really in the automotive domain and cars and systems, the digitalization is becoming a really, really big thing, especially with these driver assistance features. And it's really trending into a lot more compute inside a vehicle. And it's a lot of different functions that have to be guaranteed. And in all of these systems, there are definitely some requirements that have to be upheld. So efficiency is a very key feature here, and security as well. But one of the big important items for these this automotive domain is that these systems remain real time, so that you're sure that the tasks that need to be executed in those in critical bounds are executed within that time frame. And additionally, safety has to be guaranteed. So if something goes wrong or something breaks, we can ensure that it continues operating correctly within the system. So one of the big trends that we have been seeing this morning as well in the keynote is that with all these additional features, there's a lot of different individual chips that get created, that get integrated into the vehicles, but that's becoming a bit of a problem. So we're tending more towards a centralized approach. We're integrating everything into one system or one mixed criticality SoC. So with these applications, so for AI driver assistance or even autonomous driving, it's becoming more demanding, but this federated approach where you have individual chips doing these individual tasks, it's already becoming quite of an issue. So having all the engine control unit or entertainment systems or others individually. So what we're seeing is a trend towards these mixed criticality systems where everything sort of gets grouped into one for domain control. And here still, this safety and this real time is not negligible. So to illustrate this a bit more, I'm going to just pick out a few of the different applications. So we can have, in such a chip, we'd have to do a sensor data acquisition, some critical control task, maybe based on that sensor data. You might want to have an entertainment system on top of it, or even navigation for a driver or other assistance features. And sort of wrapping this all into one big block becomes a bit of an issue, and we see some things might get lost. So one of the main points that we're looking into and we're pushing for is splitting these all out and really going for a more individualized and isolated approach to ensure that these different tasks don't interfere with each other. So here really isolation is key to avoid this interference. So you can have like non-critical workloads in one corner, general purpose OS running your entertainment navigation in another, and ensuring this interference freedom for your safety critical and timing critical tasks. And what we're looking at is really the a physically separated control processor, which tends to be a common solution for this type of automotive SoC. Looking a bit closer at the requirements for this block, we really have, again, this physical isolation, so this independent unit. It really needs to support all the hard real-time environment. So we want tight execution bounds to ensure the tasks are executed. We want low instruction fetch delay, low memory access delays, quick reaction to interrupts and low context switching overhead. And additionally, we want to be safe, so we want to execute reliably and continue operating. And this really is where SentryCore comes in. So SentryCore is a standalone IP for this reliable real-time compute, where we have a physically separated, essentially a mega IP with self-contained processing. There's a local instruction and data memories. We have support for CLIC and other real-time extensions, and ECC-protected memory, and lockstep execution. All right, so let's dig into this a bit more. Let's build this processor system. Start out with a processing core. This is a CV32 E40P-based core, 32-bit RISC-V embedded processor from the Open Hardware Group, with 32-bit IMFC support and some additional extensions. Connecting to this, we add a tightly coupled instruction and data memory. This allows for really local computation, so no interaction with the remaining system to continue operating and processing the tasks that need to be done. Of course, we can't operate in isolation in this mixed criticality system, so we also add an AXI interface to interface with the remaining SoC that directly allows it to be easily plugged into larger systems. Additionally, to this, we add some small peripherals, so some control registers, timer, boot ROM, a JTAG for debugging, and just to support the entire SoC. Now, this is really the base platform that we start off from. And the next step really is integrating real-time capabilities. So we start this by modifying the processor core or replacing it with an extended version of the CV32, which is a CV32RT. This core, the first main benefit that it has is support for the core local interrupt controller, or the CLIC. This really allows for multiple fast interrupts and vectorized interrupt support, and this efficient configuration and support for various other extensions within the processor to allow it to efficiently process these interrupts. Additionally, this processor core also adds a custom extension on top, which is a fast RRQ extension. This really allows for a reduced interrupt latency, so it lowers that to below 6 clock cycles, and it really allows for a very fast context switch in less than 110 clock cycles. Now, this really allows us to react quickly to various interrupts and continue executing our critical tasks. But if something were to go wrong, for example, some radiation or a particle hits and we create a bit flip within the system, the entire coprocessor may crash, so we need to make sure that it can continue operating in this critical environment. So this is where we integrate really architectural reliability mechanisms, starting off with the processor core, where we replicate the entire processor and add a triple core lockstep unit around it. What this really provides is for identical execution within the 3 processors. This unit gives each of the processors the same inputs and votes on the outputs. And now if something were to fail in one of the processors, the tasks can continue operating. And once outside of a critical section, a resynchronization can be launched that within less than 600 clock cycles allows all 3 cores to get back into sync and continue processing correctly. Additionally, one of the largest parts of the IP itself is the memory, and to ensure that this is protected as well, we add some ECC protection encoding and decoding units. This is with CIO code adding 7 additional bits on top of 32 bits, allows for single error correction and double error detection. Additionally, there's a read modify write unit for efficient subword writes, so if not writing the full word. And we also have a scrubber for each memory bank that allows us to continuously check and correct any errors that are accumulating within the memory bank to avoid multiple errors affecting our processing. Now, additionally to this full system, we add an independent DMA unit or an intelligent DMA unit into the system that offers efficient transfers into and out of the system, so it is connected to our main system bus, but also allows it to access data outside and get it into the SoC for large data copies. And additionally, we provide on top of it a real-time extension, is what we're calling it, that allows for efficient sensor data collection, really collecting information from various sensors throughout the system and bringing them into our local context so that our processor core can continue executing, continue doing the tasks that it needs to without having to worry about long latencies outside the system, collecting the sensor data it needs. Now, wrapping this whole thing up, putting it inside a box, this is really a standalone unit itself, or the SentryCore unit. But looking at this in isolation is, it can work, but of course we want to integrate it into a mixed criticality system. And that's exactly what we did with our car field SoC. So putting it in here, there's a rough block diagram of car field with the safety island, of what we call the SentryCore, inside the system. Now, there's a lot going on here. I'm going to quickly just split it up into a main computing block and some additional clusters for acceleration. And the main computing system, we have a host system that is really Linux capable and based on CVA6 and has a variety of other security features and peripherals and memories for proper functionality. We can look at this more in a physical layout. This SoC was taped out last November, where in the center of it we have our host system with a predictable AXI interconnect. Connect to it, we have an OpenTitan subsystem for security, and here the safety island or SentryCore, which really allows for the whole system to have this real-time response to the various interrupts throughout. Additionally, there's a large memory inside for local data storage. We have 2 processor clusters for various compute offloading to allow for higher performance calculations. And finally, we also connect to it various peripherals and watchdog timers for proper operation. Looking a bit closer now, again, at SentryCore and the implementation here. This was implemented in Intel 16, and the configuration that we have here is without a DMA unit, but with a total of 128 kilobits of the ECC protected memory and a 64-bit AXI interface. Additionally, the 3 processor cores are physically separated to ensure that if anything affects one processor core, it doesn't directly affect all 3 of them to avoid multi-errors in the processors. Finally, this was implemented up to synthesized for 500 megahertz and fits into an area of 0.42 square millimeters with a preliminary power estimate of around 50 to 70 milliwatts. I believe this actually recently came back, this SoC, so we're really looking forward to testing it and seeing how well it works in the coming weeks. Now, hardware is nothing without software, so we also have some software support within the system with a bare metal runtime supporting 2 different boot modes inside, so either directly for debugging from JTAG or allowing our host system to start up the SentryCore with an external memory pointer. Furthermore, we already have support for a few real-time operating systems within the system, so FreeRTOS, one of the most popular real-time operating systems. Additionally, we already also have ThreadX support, which is an ASIL-D certified real-time OS, and we're also looking at RTIC, a Rust-based real-time operating system that allows for memory-safe implementations. All right, concluding, when presented here, SentryCore, really a safe and real-time 32-bit RISC-V mega IP that really allows us, it's really a self-contained IP for physically partitioned mixed criticality systems. It has a lot of real-time capability with the local memory for CLIC and various custom extensions for limited worst-case bounds, as a low interrupt latency of less than 6 cycles, a fast context switch less than 110 cycles, and additional dedicated DMA unit for data collection from throughout the SoC. It also offers reliable execution with triple-core lockstep and ECC protected memory, and it's all available on our GitHub from Pulp platform. So feel free to go have a look and try it out. Additionally, we're also looking at extending this still a bit. So one of the first things that we're looking at doing is providing support for alternate cores, or also reducing the cores to only 1 if the triple core is not needed. Additionally, for more reliability, we're looking at extending the bounds from the processor core and the memory into the interconnect and then the other registers and the CLIC and the DMA and timers within the next few months. Finally, we're also, of course, always welcome to have support from the RISC-V community. Trying this unit out, again, it's open source, happy to receive any GitHub issues. If you have any extension ideas, also pull requests are very, very welcome. And we're also starting to, our safety certification might also be something interesting to look at in the future. Now, I'd like to thank, of course, the collaborators on the project and the entire Pulp team for making this possible. We also have a booth at the event, and I think that's it.